One of the strangest experimental results ever observed has got to be that of the single-particle double-slit experiment. It is one of the most stunning illustrations of how the quantum world is very, very different from the large-scale world of our physical intuition. In fact, it hints that the fundamental nature of reality may not be physical at all, at least in any sense that we're familiar with. Theme music. Let's start with the familiar. In fact, let's start with a rubber ducky. It bobs up and down in a pool, causing periodic ripples to spread out. Some distance away, those waves encounter a barrier with two gaps cut in it. Most of the wave is blocked, but ripples pass through the gaps. When the new ripples start to overlap each other, they produce this really cool pattern. It is called an interference pattern. It is due to the fact that in some places, the peak of the ripple from one gap stacks on top of the peak from the other gap, making a more extreme peak. But when the peak from one wave encounters the trough from another, they cancel out, leaving nothing. Destructive interference. So we have these alternating tracks of wavy and flat water. Any type of wave should make an interference pattern like this. For example, water waves and sound waves, but also light waves. This double-slit interference of light was first observed by Thomas Young back in 1801. A source of light passing through two very thin slits produces bands of light and dark stripes, alternating regions of constructive and destructive interference. On a screen, of course, we now know that light is a wave in the electromagnetic field, thanks to the work of James Clerk Maxwell a century later. So it makes perfect sense that it should produce an interference pattern, right? But wait, we also know that light comes in indivisible little bundles of electromagnetic energy called photons. Einstein demonstrated this through the photoelectric effect, but his clue came from the quantized energy levels of Max Planck's black body radiation law. Check out our episode on this for the details. Okay. So each photon is a little bundle of waves of electromagnetic field, and each bundle can't be broken into smaller parts. That means that each photon should have to decide whether it is going to go through one slit or the other. It can't split in half and then recombine on the other side. That shouldn't be a problem as long as you have at least two photons. One photon passes through each slit, and then the two photons interact with each other on the other side and produce our interference pattern. But here, we get to one of the craziest experimental results in all of physics. The interference pattern is seen even if you fire those photons one at a time. Well, let me back up a bit. The first photon is detected as having arrived at a very particular location on the screen. The second, third, and fourth photons. Also, they deliver their energy at a single spot, and so they appear to be acting like particles of well-determined position. But check it out. If you keep firing those single photons, you start to see our interference pattern emerge once again. By the way, Veritasium actually conducts this experiment in his excellent series on the double-slit experiment. Really worth a look. This is so bizarre. This pattern has nothing to do with how each photon's energy gets spread out, as was the case with the water wave. Each photon dumps all of its energy at a single point. No. The pattern emerges in the distribution of final positions of many completely unrelated photons. How can that be? Each photon has no idea where previous photons landed or where future photons will land. Yet each photon reaches the screen knowing which regions are the most likely landing spots and which are the least likely. It knows the interference pattern of a pure wave that passed through both slits equally, and it chooses its landing point based on that. It turns out that the photon isn't the only thing that does this. Shoot a single electron through a pair of slits and it'll also appear to land at a single spot on the screen, but fire many electrons and they slowly build up the same sort of interference pattern. This crazy effect has even been observed with whole atoms, even whole molecules. Buckminster fullerene, buckyballs, are gigantic spherical molecules of 60 carbon atoms and have been observed to produce double-slit interference under special conditions. We have to conclude that each individual photon, electron, or buckyball travels through both slits as some sort of wave. That wave then interacts with itself to produce an interference pattern, except that here, the peaks of that pattern are regions where there is more chance that the particle will find itself. It looks like a wave of possible undefined positions that at some point, for some reason, resolves itself into a single certain position. We also saw this waviness in position when we talked about quantum tunneling. In fact, several quantum properties like momentum, energy, and spin all display similar waviness in different situations. We call the mathematical description of this wave, like distribution of properties, a wave function. Describing the behavior of the wave function is the heart of quantum mechanics. But what does the wave function represent? What are these waves of or waves in? Let's start with what we do know about the double-slit result. We know where the particle is at both ends. It starts its journey wherever we put the laser or electron gun or buckyball trebuchet, and it releases its energy at a well-defined spot on the screen. So the particle seems to be more particle, like at either end, but wave, like in between. That wave holds the information about all the possible final positions of the particle, but also about its possible positions at every stage in the journey. In fact, the wave must map out all possible paths that the particle could take. We have this family of could-be trajectories from start to finish. And for some reason, when the wave reaches the screen, it chooses a final location, and that implies choosing from these possible paths. So what causes this transition between a wave of many possibilities and a well-defined thing at a particular spot? Within that mysterious span between the creation and the detection, is the particle anything more than a space of possibility? Okay, we're adding more questions than we're answering. We still couldn't figure out what the wave is made of. In fact, the answers aren't known, but the various interpretations of quantum mechanics do try. Let's talk about the view favored by Werner Heisenberg and Niels Bohr, who pioneered quantum mechanics at the University of Copenhagen in the 1920s. The Copenhagen interpretation says that the wave function doesn't have a physical nature. Instead, it is comprised of pure possibility. It suggests that a particle traversing the double-slit experiment exists only as a wave of possible locations that ultimately encompasses all possible paths. It is only when the particle is detected that a location and the path it took to get there are decided. The Copenhagen interpretation calls this transition from a possibility space to a defined set of properties, the collapse of the wave function. It tells us that prior to the collapse, it is meaningless to try to define a particle's properties. It is almost like the universe is allowing all possibilities to exist simultaneously, but holds off choosing which actually happened until the last instant. Weirder, those different possible paths, those different possible realities, interact with each other. That interaction increases the chance that some paths become real and decreases the chance of others. There is an interaction between possible realities that is seen in the distribution of final positions in the interference pattern. That pattern is real, even though the vast majority of paths involved in producing the interference never attain reality. In the Copenhagen interpretation, that final choice of the experiment of the universe is fundamentally random within the constraints of the final wave function. The theory of quantum mechanics produces stunningly accurate predictions of reality, and it is completely consistent with the Copenhagen interpretation. But this is not the only interpretation that works. There are interpretations that give the wave function a physical reality. Remember, we know that light is a wave in the electromagnetic field, and quantum field theory tells us that all fundamental particles are waves in their own fields. This may give us a more physical medium that drives these waves of possibility. And if you thought the Copenhagen interpretation was freaky, wait until we get to the many worlds interpretation, which we will right here on Space-Time. Thanks to the Great Courses Plus for sponsoring this episode. The Great Courses Plus is a service that allows you to learn about a range of topics from educators, including Ivy League professors and other teachers from around the world. Go to thegreatcoursesplus.com/spacetime and get access to a library of different video lectures about science, math, history, literature, or even how to cook, play chess, or become a photographer. New subjects, lectures, and professors are added every month. I have recently been exploring the Great Courses Plus quantum mechanics content. It is a thorough review of a very complicated subject matter. With the Great Courses Plus, you can watch as many different lectures as you want, anytime, anywhere, without tests or exams. Help support the show and start your 1-month trial by going to thegreatcoursesplus.com/spacetime.ok. Let's look at some of the comments from our episode on the role of Jupiter in the formation of our solar system. Jason Blank asks, wasn't Jupiter almost a star? Well, the lowest mass stars are around 7.5% the mass of the Sunday, while Jupiter is 1/10,000th of a solar mass. So it is not really all that close. You'd need around 75 Jupiters piled on top of each other to ignite sustained fusion in its core. A few of you wonder why we think Jupiter even needs to have a rocky core. Well, the Sunday and other stars don't need rocky cores because they are massive enough for all of that gas to collapse by itself. There is a minimum mass that is capable of doing that. It is called the Jeans mass. It depends on cloud size, temperature, rotation rate, and composition. For typical interstellar clouds, the Jeans mass is quite a bit smaller than the Sunday's mass, but still much, much larger than Jupiter's. For Jupiter to form its giant ball of gas, it needed a rocky core to start the process. That core may have dissolved since Jupiter first formed. Juno will figure that out by carefully mapping Jupiter's gravitational and magnetic fields. Bike Jake would like me to talk more about resonant frequencies. My pleasure. A resonant frequency is when two orbiting bodies have orbital periods that form a neat ratio of small integers. For example, for every one orbit of Jupiter's moon Io, its moon Europa orbits twice and Ganymede 4 times. For every 8 Earth orbits, Venus does 13. These integer ratios maximize the amount of time that the planets spend in closest proximity. When these bodies are closest together, they have the strongest gravitational pull on each other, and that pull stops them from straying out of that resonant frequency. An imposter complains that the Jupiter episode was way too understandable. Don't worry, we've got some incomprehensible content coming your way real soon.